we knew.
Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So previously we talked about the first law of thermodynamics for a closed system where internal energy changes as a function of heat and work. And so we got this equation, delta U is QP plus W, which can also be written as delta H minus P delta V, right? But if delta U or delta H is negative, do we know whether or not a reaction will occur? And so a term that I'm going to introduce here is spontaneity. So if a reaction is spontaneous, it means that it will occur. So don't confuse this with something spontaneous being something that occurs immediately, because that's not true. And so thermodynamics only tells us initial and final states of a reaction, and it's time independent. But kinetics tells us the pathway of the reaction, and it's time dependent. And so when we talk about spontaneity in thermodynamics, we're not talking about anything that's related to time. It's just whether the reaction occurs or not. But looking at delta U and delta H alone does not fully describe a system. We need to look at another property of the system to describe the likelihood or probability that the system will be in a particular state. And this property is called entropy, and it's given the letter S. Knowing both delta U or delta H as well as delta S of the system provides information on how the system will change. And so now let me introduce you to what entropy is. It's often talked about as disorder, where if you go from an ordered molecule, in this case let's say ice, to disorder where they're broken up into their individual molecules and we're going from a solid to a liquid, there's an entropy change that is positive. But another way that I want to describe entropy is the number of ways of achieving a given energy state, which is called degeneracy. Which is the number of ways to achieve a given energy state. Degeneracy is given the symbol W, but don't confuse it with work. They're completely different things. So the relationship between this degeneracy, which is the number of ways in which you can achieve a given energy state, and entropy, which is the number of ways in which you can distribute that energy, is given in the Boltzmann equation. Which says S, or entropy, is the Boltzmann constant multiplied by the natural log of the degeneracy. So this part is statistical, and this part is a thermodynamic property. And so when we calculate the degeneracy, let me show you an example of that. So I'm going to draw out a flask like so. And let's say there's two molecules in a flask with two equivalent same energy states on the left and on the right. And so in this flask, there's two spots in which these two molecules can be distributed. So the first arrangement can be A and B in the same left state, right? What could another arrangement be? We could have A and B both in the right. Excuse these not the best diagrams, but another state would be A being in the left and B being in the right. And you guessed it, the final thing that we can have in terms of the way in which we can distribute A and B is B being in the left and A being on the right. So this can be called microstate 1. This can be called microstate 2, microstate 3, and finally microstate 4. And all of these microstates have the same energy. So like enthalpy and internal energy, entropy is an extensive property. And so what that means is that the total entropy can be written as S1 plus S2. And then if we rewrite this in terms of the Boltzmann equation, we can get KB ln W1 plus KB ln W2. And since these are both natural logs, we can combine them by putting KB as the constant and then doing the natural log of W1 multiplied by W2. And this represents the total degeneracy. So another important thing is that in an isolated system, where remember the energy is constant, at equilibrium the degeneracy is at a maximum. So degeneracy is at a maximum in an isolated system at equilibrium. So finally, I wanted to talk about how molecules in a gas phase occupy many more states than liquids and solids. So when we look at the Boltzmann equation, S equals Kb ln W, we can actually rank gases, liquids, and solids based upon these values. Let me show you that right here, where the degeneracy of a gas is greater than the degeneracy of a liquid, which is greater than the degeneracy of a solid, since molecules in the gas phase can occupy many more states. So if you think about it in terms of a beaker, if you have solids, you have a limit to how much space they can occupy, right? But when you have a gas and they're much more spread out, they can occupy many more different states. So there's small errors in entropy, but large errors in the statistical state, which is degeneracy. And so when we talk about entropy, the entropy of a gas is way bigger than the entropy of a liquid and the entropy of a solid. So the trend is the same, where it's decreasing, going from a gas to a solid, but when we talk about entropy, the entropy of a gas is much greater than the entropy of a liquid than when we talk about the degeneracy, which is looking at it in a more statistical way in how many areas the gas can go.